Alright, for this question, the input is a sinusoidal waveform. So we're going to bring every component into the frequency domain, and we can solve the circuit. So first question is asked to find the Thevenin voltage. The second one is Thevenin impedance and Thevenin equivalent. So these two are going to form that one. So just a quick review. You should learn this in year 1. So if we have this VTH and we can have this impedance ZTH, then this is the Thevenin equivalent circuit. Okay, so the VTH can be found when the circuit is open, so it's open circuit. It just equals to VAB here for this particular example. Okay, equal to VAB. All right. So the Thevenin impedance is that TH. So this one we can find by set the voltage source to 0. Okay, to 0. So it's equivalent to short circuit. So we're going to short circuit this one to get that. If you got a current source in the circuit, so you will set the current source to the current source to 0 as well. So that will equivalent to an open circuit. Okay, if you have a current source like that, you just make it an open circuit. Okay, so that's the background. We're gonna do that. So first, how can we find the VAB here? Okay, so we're gonna make some equivalent. So we're gonna call this one Z1. So this impedance called Z2. Okay, so for that one, we learned that for capacitor is 1 over J omega C. Okay, for Z2, that is J omega L. Okay, so we plug the J and omega in. So omega is 400. So omega here is 400 from this equation from the source. Then we plug numbers in. We will got that the first one, Z1, gonna equals to negative JAT, and this Z2 equals to a positive J160. Okay, so the inductor always be positive, the capacitor always be negative J, because you can see that there is a J there. So if we multiply J bottom and top, then you will find is equals to a negative J. Okay, all right, so after that we're going to simplify the circuit. All right, to let me scroll down a little bit. So to find the voltage here, first we want to combine these two. Okay, we want to combine these two, so we can have a resistor there, and we can have a combined impedance, and the voltage here for VAB gonna become a voltage divider, right? So this is the voltage VG, and it will cross this two, and the voltage shared on this Z gonna be the VAB. Okay, that's the idea. So the first step is we're gonna find this Z. This Z equal to Z1 in parallel with Z2, and if you remember, the equation for that is Z1 multiplied with Z2 over Z1 plus Z2. Okay, and Z1 multiply with Z2, so Z1 is negative JAT multiply with a J160 divided by So negative AT plus positive J, so it's positive JAT. Okay, then we can cancel this AT, and 2J becomes a negative 1, and there is another negative sign, so this one become positive, right? So this is a positive 160 divided by J. Then we talked about this. J equals to, sorry, let me scroll to the right a little bit. So then we multiply bottom and up, so J square. So this one gives us negative 160J. Okay, so this becomes a negative sign. Alright, so we got this one. Then the voltage VAB just equals to VG multiply with the voltage divider here. Okay, this is a 360 and this is a negative J 160. We got that. So VJ equals to Z over R plus Z. Okay, so that becomes VJ multiply with negative 160J over what's that, 320 minus 160J. Okay, then we want to find how much is the VG. Okay, so now we don't know what is VG. So VJ is 50 sine 400T volt. Okay, so if you follow the textbook convention, we always talk about cosine. So you want to convert that one to a cosine. Okay, so if we how to convert a sine to a cosine, so you can see sine is something like this. Okay, that's a sine. So cosine is start from here. Okay, so it's like the sine shift to the left, or you can say, sorry, you can say it's a cosine. If you start with a cosine, you're going to shift it to the right for 90 degree. Okay, so you will have the same 50 cosine 400T. You want to shift to the right for 90 degrees minus 90 degree. Okay, if you want to convert this one to a polar form, that's equals to 50, that's the magnitude, and the 90 degree. Okay, so how that looks like. So the 90 degree, you can think in the complex plane. So the vertical is the imaginary part, this is the real part. So negative 90 degree is actually so if you say this one is positive J, this one is positive 1, sorry, is a positive 1, and this one is negative 1. So this one, negative 90 degree, is actually negative J. Okay, so if you see this one equals to 50, sorry, I will say negative J 50. Okay, then let's plug everything into this one. So this one become negative J 50 multiply with negative J 160 and divided by 3 minus 160J. Okay, so this 2 will becomes negative 1, and multiply with another negative. They cancelled, so only one negative sign left, and we can cancel this 160 as well. So 160, then there's a 2 left. Then we clear the term. We got negative 50 on top. Okay, that's the only thing left. At the bottom is 2 minus J. Okay, that's what we got, and we can multiply both sides with a 2 plus j. That's the trick we're going to use. Okay, so this thing at the bottom becomes this a squared minus b squared thing. Okay, then in the bottom we got 2 squared minus j squared. So j squared is -1. -1 plus another negative sign become positive. So bottom's a 5, and the top is -100 minus a j 50. Okay, so because bottom is a 5, then we can got this one equals to -20 minus a j 10. Okay, that's the first question. This is the VAB. Okay, so just quick review. So the VAB, the Thevenin equivalent voltage, is the open circuit voltage, and if you want to know the open circuit voltage here, you want to combine these two first, so it's become a voltage divider. So the output voltage equals to this VJ being divided by this 2 voltage divider, then we can use that to calculate the VAB. Alright, so this is how we do the part A. So for part B, to find the Thevenin impedance with respect to the terminal AB. Alright, we talked about this. So for the impedance, we're going to set the voltage source to 0. Okay, let me change the color. So for part, so for part B, okay, sorry, we need to see that. So for part B, we're gonna set that one to a short circuit. Okay, so then just short circuit, and then we got this one, we got this Z1, and we got this Z2. We all know how much are they. Okay, so that's the A and a B. Okay, so what the total impedance of this circuit is going to be the ZTH. Okay, so we know this is 320. We know this one is J negative J80. This is positive J160. So the ZTH equals to 320 in parallel with Z1 in parallel with Z2. Okay, so we already know Z1 parallel with Z2 is something we already done here, is -160. Okay, it's here. So we can just make it equals to 320 in parallel with negative J160. Okay, so let's do this. To do a parallel is just 320 multiplied with a negative J160 and 320 plus, which is minus J160. Okay, and we can see here is 160, so this is become a 2. Then this one, I will write it down here. Okay, so this one becomes 320 multiplied with negative J. Okay, that's the top, and the bottom is 2 minus J. Okay, and again we're gonna multiply with a 2 plus J on the top and the bottom. So the top becomes negative J640 plus 320. The bottom is 4 plus 1. Okay, so it's a 2 square plus a J square. Sorry, 2 plus a 2 square minus a J square. Okay, then we got the final answer, 64 minus J120A. Okay, this is a part B. Okay, and so this is the part B, and the last part is the part C. So we just put everything together. Okay, part C, we have a Thevenin equivalent voltage, which is equals to, how much is that? It's negative 20 minus J10, and we have a Thevenin equivalent impedance, which is equals to 64 minus J 120A, and that's it. That's the Thevenin equivalent. Okay, let me maybe shrink this a little bit so you can see, hope you can see the whole solution down here. Okay, I'm not sure if it's clear enough.